good morning everyone. Once again, welcome to the world of electronics. Our lesson for today is all about capacitive power supply. Basically, there are two classes of power supply. This is in accordance with the methods of stepping down the voltage from the AC source voltage or from the outlet. These two power supplies are the inductive power supply and the capacitive power supply. A power supply is said to be inductive when the AC source voltage from the outlet, which is 232 volts AC, is lowered down into 13.5 volts AC. The voltage is lowered down by means of magnetic induction, and this is done by a transformer. On the other hand, a power supply is said to be capacitive power supply when the AC source voltage from the outlet, which is 232 volts AC, is stepped down or lowered down into 13.6 volts AC by means of capacitive reactance, and this is done by a capacitor. Our lesson for today's class will be focused on a capacitive power supply. Basically, capacitive power supply is also known as transformerless power supply, in the sense that a power supply doesn't use a transformer in stepping down the voltage, but instead a capacitor. Basically, there are four stages of this capacitive power supply. There are four stages. Wherein the first stage is a step down stage, wherein the AC source voltage from the outlet, which is 230 volts AC, is lowered down into 13 volts AC before it is fed to the rectifier stage. The rectifier stage will convert this AC voltage into pulsating DC. That is now the operation of the rectifier stage, converting AC into DC, pulsating DC, before this pulsating DC is fed to the ripple filter. This is now the rectifier stage, followed by a ripple filter stage. The ripple filter stage will smooth out the pulsating DC into a varying DC. Then finally, this variation of DC voltage will be fed to the final stage, which is the regulator stage, wherein the variation of DC here is held constant at the output by this regulator circuit or regulator stage. In short, the AC voltage here is converted into DC. Then actually we have here a basic circuit of a capacitive power supply. The first is the AC source. We have here the AC cord, symbolizes the AC source. Then, it is followed by a capacitor. A capacitor here is a voltage dropper that will lower down the voltage from the outlet. If the voltage here is 230 volts, then this capacitor will drop an amount of voltage that will provide a desired lower amount of voltage at the output. So it is actually paralleled with resistor. Then the other line here is a resistor again that will limit the amount of current that will flow around the circuit here. This is to prevent the harmonic distortion. So we will explain in detail later on what is this harmonic distortion caused by the circuit. Then followed here by the rectifier circuit. There are actually 4 diodes or 4 rectifier diodes that are connected in inverse connection. Okay, maybe here. Then we have here a capacitor that serves as a supply filter capacitor. Then finally, a diode, which is a voltage regulator, before it is supplied to the load resistance or RL. We have here the positive side, and over here is the negative side. RL here is actually the appliance protector circuit that will consume the current, and it is designated as RL or load resistance. So we have here the necessary electronic components for the circuit. At first, before we assemble the circuit, it is very important for us to determine the amount of the voltage to be supplied to the load. So this appliance protector circuit needs 12 volts. 12 volts. That is why we prepared a Zener diode here, wherein the specification rating is 1N 4742. This is 1 watt, and the Zener voltage is 12 volts. Necessary for this load resistance, which is the appliance protector circuit. Okay. So, how much would be the capacitance of this capacitor as a voltage dropper? So, we need to compute that. So, the formula would be, we have to get first the peak value, because the voltage that is measured at the outlet, which is 233 volts, is just a root mean square or RMS value. No? 233. But we will use 230 as a standard voltage at the outlet, because the voltage at the outlet is prone to variation. Sometimes 220, sometimes 240. So the voltages there will vary between these two voltages. So we will just get the average voltage, which is 230. So the formula to get the peak value is BRMS times the square root of 2 or 1.414, which is a constant value. So the RMS here is 230 volts times 1.414 is equal to 325 volts. Then, after you got the voltage peak value, we will now proceed to the voltage that will be dropped by this capacitor. So, the formula would be voltage across this capacitor is equal to so we still need to compute the voltage across this capacitor. So the next procedure after getting the peak value is to get the voltage across this capacitor. So it goes like this. Peak value minus 1.4 volts plus the voltage for the general diode that is at the output. So the peak value now is 325 volts minus 1.4 plus 12 is 13.4 volts. Where did we get this 1.4 volts? Actually, that is the total voltage of the two diodes of this bridge configuration. So it goes like this, class. In the first half cycle, the polarity goes like this. Negative, positive. So we will adapt the flow of electrons, not the conventional flow, which is the flow of the protons. So the current would flow here. It flows here. Once this is negative and positive here, the current would flow then to this diode because it is forward bias for this polarity, negative, then the cathode is negative. Then it flows here. It is smoothed out by this capacitor. Then it is regulated by this diode. Then it goes here. So two diodes are conducting simultaneously or at the same time. Therefore, because the forward bias voltage of these diodes, each diode will drop 0.7 volts. 0.7 volts, 0.7 volts, and 0.7 volts. Two diodes are conducting at the same time. So therefore, 0.7 plus 0.7 is 1.4. Plus the voltage across this diode. Because this general diode, the general voltage is actually 12 volts. So, 12 volts plus 0.7 is 12.7. 0.7 plus 12 is 12.7. Then another 0.7 is what? 13.4 volts. So this is now actually the output voltage, 13.4 volts. No? Okay. So 325 volts minus 13.4 volts is equal to 311.6 volts. If you are going to deduct 355 volts by 13.4 volts, is equal to 311.6 volts. That is the voltage across this capacitor. Okay? Then, we will now come to the resistance. What should be the capacitive reactance? That is XC. The unit is ohms. Or, it can be considered as R, resistance. XC is equal to the voltage across capacitor over the current rate. The current rate is actually 0.055 amperes. That is the current rate required by the load resistance. So this appliance protector circuit needs at least 55 milliamperes or 0.055 amperes. Okay. So, the voltage across here is 311.6 volts. Divided by 0.055 amperes, the result would be 5,665 ohms. That is now the capacitive reactance. The capacitive reactance of this capacitor here. Okay? Then, the next procedure here, or the next step, is to determine the capacitance. What should be the capacitance of this capacitor? So, Xc is equal to 1 over 2 pi Fc. What is unknown here is the C, or the capacitance. We got already the Xc, or the capacitive reactance. So therefore, let us derive the formula to get the capacitance. C is equal to 1 over 2 pi Fxc. No? Fxc. So by substitution, we have here 1 over 2 times 3.14 times the frequency. The frequency actually here is 60 Hz. Because if we are going to measure the frequency, let us set this digital multimeter to frequency meter. Then insert the two test rods to the outlet in such a way that the frequency is displayed, and it is 59.8 Hz or 60 Hz. That is now actually the frequency distributed by the electric company in the Philippines, 60 Hz. So therefore we have here the frequency is 60 Hz. No? So 1 over 2 pi Fxc. So 2 times 3.14 for the pi, frequency 60 Hz, times Xc, which is 5665 ohms. So if we are going to multiply all of the values here, the result would be 1 over 2,134,572. So 1 divided by 3 million or 2,134,572 is equal to 0.00000047 farad, or 1, 2, 3, 4, 5, 6, that is 0.047 microfarad. So that is why the capacitance of this capacitor here is 0.47 microfarad. That is why we are using here 474J. So that is now the numerical code of this capacitor, which is equivalent to 474. 4 there is the number of zeros, that is 470,000 picofarad. When we convert it into nanofarad, that becomes 470 nanofarad. Or when we convert that one to microfarad, that becomes 0.47 microfarad. So the value of this capacitor is actually 0.47 microfarad, which is a non-polarized capacitor. Then the working voltage given here is 630 volts. 630 volts. 630 volts. The voltage should be higher because the voltage at the source voltage or from the outlet is 230. Then the peak value there is 325. So the working voltage of the capacitor should be higher than the voltage at the input. That is why we are using 630 volts, or you may have 400 volts as long as it is not lower than 325 volts at the input. Okay. So we will now assemble the circuit. Okay, let us now assemble the circuit. We have here the AC source based from the diagram. So we will connect it here. Connect it here. Okay. This is now the AC source. Then let us connect the capacitor over here. Capacitor paralleled with resistor, which is 1 mega ohm. The colors are brown, black, green. So, just across this capacitor. Then the other line is connected with 100 ohms resistor. The colors are brown, black, brown. So let us connect here. Okay. So what is the purpose of this 1 mega ohm which is across this capacitor? Actually, this capacitor will store voltage. Then this capacitor will store voltage, which is the 0.47 microfarad. Then the stored voltage of this capacitor will be discharged by this resistor. Because without this resistor, it goes like this, class. So let us use this capacitor. Connect it to the AC source voltage. The voltage now is stored in this capacitor. The two terminals are actually connected to the two terminals at the outlet. So, let us measure the voltage. We are setting here the analog multimeter to 250 volts. So, let us disconnect. Let us disconnect these two terminals from the two capacitors terminals. Then the voltage goes like this. No? At first, so let us connect again. Okay. The capacitor now is connected to the outlet. So let us disconnect these two terminals from the two capacitors terminals. Then measure the voltage here. So there is a higher voltage stored in this capacitor, around 250 volts. No? Actually, this capacitor is stored the voltage up to the peak value. More than mga around 355 volts, which is the peak value. No? So, that is now the action of the capacitor, and it is very risky. Because if there is no capacitor, usually, then if you try to touch the terminals of this capacitor or any of the components here, you can be electrified. You can feel an intense pain on your skin as you touch the two terminals because there is still a stored voltage here. So, that is very risky. That is why there is a necessary procedure to be away from the risk. So let us first short if there is a remaining voltage here. Okay. Or over here. See? There's still a remaining voltage here in this capacitor. Okay? However, if you connect this resistor across this capacitor, then supply this with voltage from the outlet. Okay? Then after storing this with voltage from the outlet, then measure the voltage across the capacitor. So there is no more voltage stored here because the voltage stored at this capacitor is discharged by this resistor. That is now the purpose of this resistor 1 mega ohm, to the charge voltage when the circuit is disconnected from the outlet. There should be no remaining voltage at this capacitor. Okay. That is why there is a resistor connected across this capacitor. Okay. Then, let us connect again this AC cord. Okay. How about this resistor here? What is the purpose of this resistor, which is 100 ohms? The purpose of that resistor is to limit the surge current that is entering the circuit. Because without the resistor, the capacitor will introduce a harmonic distortion, which will lower down the quality of the circuit's operation. No? Okay. For example, this is now the AC with form. But without this resistor, the AC with form will become distorted. It will be going like this. We call it harmonic distortion caused by the action of the capacitor. So, the current pushed by the AC source voltage 230 volts should be limited by the resistance of the resistor to avoid this harmonic distortion in such a way that there is a higher power outputted by this power supply to be introduced or fed to the load resistance, which is the appliance protector circuit. No? That is really the operation or the purpose of this resistor. This resistor 1 megaohm is just the charger of the stored voltage of this capacitor to prevent us from the electric shock once you happen to touch any of the terminals here. Although the AC cord is already disconnected from the outlet, but there is a remaining voltage across this capacitor. So, to remove that stored voltage, so there should be a permanent resistor connected across it. Okay? Then, we call this circuit here as the step-down circuit because this capacitor will drop a certain amount of voltage to lower down the voltage from the outlet. The 230 volts here will be lowered down to 12 volts. Actually, the voltage is lowered down capacitively by the action of this capacitor. That is why we call this power supply as capacitive power supply. Then the next stage is to connect these diodes we have here. So, we have this diode. No? This diode now, the anode is connected here, over here, to the two terminals of these two components, resistor and capacitor. Then, over here, for example here, any of the holes here. Then, this one here, the cathode again is connected together with the anode here. So, we have here the anode. The cathode. Anode is here. The cathode is this one. The cathode is this one. So, just like this. Then the cathode is over here. Okay. Okay. Cathode, anode. Cathode, anode. Cathode, anode. Anode, cathode. Okay. Well, the other line connected to this 100 ohms resistor, the anode is connected to the cathode here. So, it goes like this. Okay. Anode, cathode. So, the two cathodes are connected together here. Then, the anode is over here. cathode, anode, anode, cathode. So, cathode, anode. Okay? So, anode, cathode, anode, cathode. Then, cathode, anode, cathode, anode. These four diodes will serve as a rectifier circuit that will rectify the lowered voltage here, AC voltage, into DC pulsating DC here. So, the next stage is the ripple filter capacitor. By the way, what is the specification rating of these four diodes? It is actually, or they are actually 1N4007, wherein the peak inverse voltage is 1000 volts. The peak inverse voltage is the voltage of the diode at the reverse direction, because the forward direction is actually 0.7 volts. That is the forward bias voltage of these diodes. Each of these diodes will usually introduce 0.7 volts in order to operate these diodes into full swing operation. But during reverse direction, when the polarity is inverted, the cathode is already positive, provided by the AC source here, the peak inverse voltage there should be higher than the input voltage, because the input voltage is 325. So it should be higher. How to get the peak inverse voltage? That is 325 volts as the peak value times 2 is around 700 volts, almost, no? 650 minus 1.4 volts for the two diodes that are conducting at the same time. So, the appropriate diode here should be 1N4007 or 1N4006, because it is mga around 700 volts, no? But what is appropriate here is the 1N4007, because it is almost 1000 volts. Then, we are using here a ripple filter capacitor as 330 microfarad with a working voltage of 35 volts. Because it should be 35 volts, because sometimes the voltage will increase, no? It is not only 16, but it will reach to 25. That's why it is very necessary for us to use a higher amount of voltage for the supply filter capacitor. It is actually an electrolytic capacitor. Okay. Okay, we have here. Okay, here. This should be the positive side. The two cathodes are actually the positive output, and it should be connected to the capacitor positive. Then, finally, we have here the capacitor, wherein the positive side is connected to the two cathodes that provides positive output voltage. Then, the general diode, you see that the general diode is connected in inverted polarity, wherein the cathode, which is negative, is now connected to the positive side, because the purpose of this general diode is to regulate. The general diode will operate normally at the reverse polarity. That is why we are now connecting the general diode here just across the capacitor. Okay. Let us check again. Resistor is across this capacitor, connected with AC power line here. Then the other line is connected with resistor. We have here 100 ohms. Then two diodes are connected, anode and cathode. So anode and cathode. The other line is cathode and anode. So we have here cathode and anode. The two cathodes are connected together at the output. The two anodes are connected together, and that is now the negative side of the capacitor. So, negative. Okay. Let us recheck if there are no shortings. Okay. Now, let us measure the voltage across this capacitor or general diode. Then we will measure the output voltage. Let us set this one to voltmeter DC. It is DC voltmeter. So let us measure if the voltage here is somewhere at 12 volts. Okay. Measure. Okay. Okay, there's something wrong with the circuit because the two terminals of the diodes are not actually connected to the two components, the anode region diode and the negative side of this capacitor. So let us go on. Let us transfer the connection here. It should be here. It should be here. And it should be here. Okay. Recheck again, recheck. If the four terminals are already connected together, so I am using here a long nose plier to prevent us from electric shock probably if there is still stored voltage here, but we knew that there is no more stored voltage here because of this resistor. So this is to make our connection easier. We will use a long nose plier. So recheck again if there are errors in our connections. So there is no more error. So let us connect this one again and measure the voltage across this capacitor or zener diode at the output. So it is 12.58 volts. That is now the regulated output voltage. From the 230 volts now, AC is converted into DC, then being regulated by this zener diode, and that becomes 12.71 volts. So, let us connect this one to the load. So, load resistance. So, let us disconnect this one again. Then, here, the positive out. Then, the negative output is over here. So, positive side, negative side. Then, we'll connect this one. Positive. Then this one is negative. Okay. Let us connect this AC cord to the outlet. If this appliance protector will operate. At first, okay, there is no lighting of voltage. Probably there are disconnection. Okay. Okay, let us now connect this load resistance, which is the appliance protector circuit, to prove that it is operating. That the output voltage here, which is 12 point something DC volts, once it is supplied to the load resistance, which is the appliance protector, will operate. Okay. Okay, let us connect this one again. At 5 seconds, this lid will be lighted and this will be turned off. Okay, see? That is now the action of the appliance protector circuit. Again, let us disconnect this one just in case it is blown out. Then after a few minutes probably, the electricity is coming back. Again, we will count for 5 seconds. 2, 3, 4, 5. 5 seconds. That is now the operation of the appliance protector circuit. That is to protect your appliance. For example, LED TV receiver, just like that, to protect from damages. So, that is the action of the appliance protector circuit. It delays the operation of your TV receiver to lowers down the voltage at the outlet. No? Okay. So actually, this capacitive power supply now is used to supply this appliance protector circuit, and we are successful. So without the use of a transformer, because a transformer is much bigger and it is more expensive. It worth 300 pesos. Whereas with capacitive power supply, more or less it is only 30 pesos over here. All in all, probably is only 50 pesos. But with the application of this transformer for the inductive power supply, the price is much bigger, more or less 350 pesos compared to 50 pesos only. Okay? See how useful is the capacitive power supply? Again, at 5 seconds, 2, 3, 4, 5. Okay? That's all, my friends. Okay? Next meeting, we will be discussing about the part 2. And it is the application of this power supply itself, capacitive power supply. We will use a generate which is 9 volts to be supplied to the other circuit. Okay, thank you. And so long.